Welcome to lecture 28 of Introduction to Quantum Field Theory. In this lecture, I will discuss some further properties of the ON vector model. Recall that in lecture 26, we solved the ON vector model exactly in the large N limit. We performed the renormalization of the ON vector model for zero mass in the last lecture, finding the result for the pressure that's reproduced here in equation 28.1. The parameter x that's appearing in this equation here is to be determined non-perturbatively from the saddle point condition that's reproduced in equation 28.2 here. In this lecture, I want to evaluate the result for the pressure at finite temperature using the non-perturbative solutions of the saddle point approximation. Also recall that we found the exact running coupling of the ON vector model in the large N limit was given as the following result here, where mu naught is the lambda pole of the theory that we cannot exceed in terms of energy scale. Close to the lambda pole, the quantum field theory breaks down, so we can only probe scales, energy scales mu bar, much less than the lambda pole. At finite temperature, we can choose to express the temperature T in units of the lambda pole. So we write T is lambda pole times a dimensionless number, and we write the dimensionless lambda as e to the minus chi, so that for large chi, the temperature is much smaller than the lambda pole. Of course, we can invert this result and choose to express the lambda pole in terms of the temperature T. Now, using the explicit expression for the coupling and the rewriting of the lambda pole in terms of the temperature, the pressure and the saddle point condition for the ON vector model are given by the set of these two equations that are shown in equation 28.5 and 28.6. I also want to recall that these functions JB and IB are functions that appeared throughout the course before. They are given as simple thermal integrals, and in the case of the scalar field theory in 3+1 dimensions, these can be written as infinite sums over Bessel functions K2 and K1 in the following way. I also want to recall that we had a homework problem number 11, that really involved these functions here. So looking at these two results for the pressure that is to be meant to be evaluated as the non-perturbative solution X that's resulting from this saddle point condition here, I want to just point out that the pressure P in this form is completely independent on the renormalization scale mu bar, as it should be. So a physical quantity should not depend on mu bar, and indeed the pressure written in this form here does not. It's supposed to be an exact result, not a perturbative approximation, and as such, it clearly cannot depend on the result, on the choice of an arbitrary parameter. We want to sort of solve this problem now. So just backing up on one slide, if we want to try and get a solution to the saddle point condition here, we find that X here has mass dimension 2. So the only other dimension full parameter in this equation is the temperature. So basically we can choose, or we can sort of already say that X has to be proportional to temperature squared. So we can use this result to write X as temperature squared times a dimensionless number MB. And MB now can only depend on the only dimensionless parameter that's in the game. You can think of this as being some generalized coupling, such that MB has to be a function of the parameter chi. Recall that large values of chi correspond to small energy scales and thus small coupling, low temperature. Well, small values of chi correspond to big coupling, high energy scale or high temperature, as a result of the specific equation 28.3 that we used to represent the temperature and the lambda pole. Solving the saddle point condition numerically then gives us a result for this mass parameter, and we can expect the result for that. We can, of course, convert the result back in terms of a mass parameter as a function of temperature, but just using the relation between the temperature and the lambda pole and chi. How does it look like? Here we have the mass parameter as a function of chi as a function of chi. So for large chi, remember this is small coupling, the mass parameter is small, and it grows as the coupling grows. So growing, sort of lowering chi means growing the coupling, increasing the energy scale, and we end up with values of the mass parameter on the order of 1 for chi values that are of order unity. So remember, we're getting closer to the lambda pole as we're going to the left. We can also then use this result for the mass parameter, just plug it into the pressure and find the pressure of the theory as a function of chi. I've chosen to normalize the pressure by the free pressure of the theory. So that's a non-interacting vector field, or n-component vector field. So I'll talk about the normalization being n times the free pressure of a single scalar field. Then at large values of chi, which corresponds to small coupling, this ratio just goes to 1. That just says that if the theory is free, then it just corresponds to n copies of a free scalar field. So this is just a consistency check. But we can decrease the value of chi, increase the energy scale, increase the coupling, and the result for the pressure decreases, but stays well behaved even as we sort of decrease chi to values that get us very close to the lambda pole. The upshot is that we get non-perturbative results for the pressure in the ON model. These results are well behaved and physically sensible, both for large coupling, for large chi and for small chi. In terms of the origin coupling constant, which was given by this expression here, we can again express the lambda pole in terms of chi in the following form. So if chi here is small, then the coupling constant becomes sizable, becomes much larger than 1. In particular, if we sort of choose the renormalization scale to be, for instance, 2 pi t, the lowest lying Matsubara frequency. So the point is that using the exact result in the large n limit, we get strong coupling results for the ON vector model, but the lambda pole prevents us from accessing the regime where lambda really sort of goes to infinity. Close to that point, we can't really trust the theory because the theory is breaking down. As an afterthought, I wanted to just point out that one can also set up the ON vector model in less than 3 spatial dimensions, in particular in 2 spatial dimensions. By dimensional reasons, then the quartic interaction term, the phi-4 term, has to become something like a cubic term. So we would like to study a theory that has, a sextic term. So this has a coupling constant that's phi vector to the third power. If we choose this particular coupling term, then the large n solution to this 3-dimensional ON vector model is a very special theory. It's a pure conformal theory because its conformal anomaly vanishes for all values of the coupling. As such, it does not have a lambda pole. The coupling is trivial. And we can access the strong coupling limit directly from the field theory. So I would sort of just suggest that if advanced students are interested, they can take a look at a recent study of this ON model in 2+1 dimensions, where I talk about the relation to sort of more fashionable approaches to strong coupling, such as holography. And this concludes the present lecture.